First of all, thank you for joining us on the 11th installment of the Catalyst webinar series. We appreciate everyone taking 30 minutes out of their day as we try to bring some value outside of just product information and manufacturer information. We're trying to bring some general knowledge to make us all better in this industry collectively. This is a webinar, so we'll address all questions at the end. Please type them in the Q&A or chat fields of your Zoom control panel. Our story, for anyone who doesn't know us, we are a manufacturer's rep agency, and what we do is we connect global manufacturers to the local market. Why we exist, and really our vision here as an agency, is we're trying to help achieve environmental sustainability and personal independence through electrification. So our alignment is based on products related to that. So what we're here for today, Solar 101, become that technical expert in solar installation. What we're going to look at, first off, we will touch on the history, and then we'll get into components. So we're talking modules, inverters, racking. Those are the three core components. Then the balance of systems, everything else you need to sell as an electrical contractor or electrical wholesaler to get this done. We'll quickly look at what's needed in design and then walk you through a real-world installation. And then last, we'll just touch on the CEC, that Canadian electrical code. So we can't talk about where we're going until we know where we have been, and where this all started was in 1888, really. It was a Russian physicist, Alexander Stoletov, who built the first cell based on the odor photoelectric effect. And this was discovered and proven earlier, a year earlier actually, by Henrik Hertz in 1887. Hertz became famous for proof of the electromagnetic spectrum. In 87, when he discovered this and the photoelectric effect, he was noted as saying there was no practical use. This is the same spectrum that gives us X-rays, radio waves, and everything else that we use so importantly in the electrical industry. So he said it would have no use, and Hertz also became famous because, of course, all frequencies measured in that spectrum carry his namesake, Hertz. In 1905, it was Albert Einstein who proposed a new quantum theory of light and explained that photoelectric effect for the first time ever. It was a landmark paper. He went on in 1922 to win the Nobel Prize in Physics for that paper on the photoelectric effect, or what was included in it, really where he described that light was not waves, but it was particles, it was photons, and really that photoelectric effect, means the emission of electrons or free carriers when electromagnetic radiation, like light, hits a specific material. So the energy that can be created from that. It was in 1954 that the first practical photovoltaic cell was publicly demonstrated at Bell Laboratories. Bell was also famous in a previous webinar series we ran for developing one of the first LED diodes. And then really solar gained prominence and notoriety in its usage in satellites. In 1958, solar cells were incorporated into the Vanguard satellites. Up until that point, satellite life was very short due to the battery technologies used on it. So solar deployments in satellites helped increase the longevity of those satellites. And that was 1958. And here we are in 2020. And we're really just getting into, at least in our marketplace here in Atlantic, Canada, into widespread solar deployments. This is what we're going to look at today before we get into those individual components. It's grid-tied systems. So what a grid-tied system is when the solar gets tied directly to the house. No backup power, no battery storage. The solar is tied directly to the house and then tied back to the grid. This is done through two technologies, typically net metered or a feed-in tariff. So you have a single service entrance on the home, and then from there, net credits are tracked. So essentially, when you need more power on the home than you're producing from the solar, you consume it from the utility, and vice versa. When the home or the solar is producing more power than the home is consuming, that excess power gets backfed onto the network. And I'm just going to grab my laser pointer here real quick just to give you an idea of this single line diagram. So this is a typical grid tied system. So you have your modules or panels on the roof. You have some sort of junction box to take that wiring, typically only 4 wires, or in the case of microinverted 2 wires, you'd have coming off the roof. So that would be in a transition box in or outside the home. From that transition box, you would go to a disconnect if it's a DC system off the roof, so a DC disconnect. From there, you would go to your inverter. Out of the inverter, you would go to a utility disconnect switch, typically by the meter, and then from that disconnect switch, you would go back into the breaker panel, and from that breaker panel, that's how power would get back out onto the grid tied system through that bidirectional or net meter. So that's a typical wiring diagram. Now let's look at the modules, the common modules. And I do want to point out module is the proper terminology. Panel, the industry has tried to move away from that because of its association with the electrical panel. So in the modules, you've got monocrystalline, polycrystalline, you also see thin film. We won't really talk about thin film. You'll see this in RVs, portable, anywhere you need smaller or temporary, portable, anything that needs to be flexible. That's where you see thin film used. What we use in all grid-tied systems, or you'll use in all grid-tied systems, either mono or polycrystalline. And mono is the most efficient, but the most expensive. It's also the newer technology now. Pricing, because of economies of scale, has come down quite a bit. But mono is easy to tell by its characteristics. Mono has a black cell. If you can see here my laser pointer, you'll see that identification is pretty clear. And then polycrystalline is that blue cell. Now, both modules come in the same physical form factor. Those form factors for residential and commercial deployments are measured in what they call 60 or 72 cells. So a 60 cell, if you can see here, this is one cell. So a 60 cell would be 6 cells across, 10 rows tall. That would equal 60 cells dimensionally. That's 40 inches by 65 inches. And then on a 72 cell, you would have 6 across, but you would have 12 tall, would give you the 72 cells. So all comparisons by manufacturers are made on those two form factors, 60 cell and 72 cell. And then wattages and efficiencies vary. The first cells ever created, as we looked at the history, were less than 1% efficient. Now we're pushing 20+ efficiency on cells. And when you do purchase modules, they are measured in watts. And right now, 60 cells available on the market, not what a manufacturer may publish on their website or tell you is conceivable or what's coming down the pipeline, but what you could actually buy today in a 60 cell, you're ranging from 250 to 325 watts, and a 72 cell from a power perspective is ranging from 300 to 400 watts. So that's the modules. Pretty simple, pretty straightforward. Not a lot to differentiate there other than price. The next core component, so I've got my module up on the roof. What's my opportunity on the other side? I need my inverters. And there's really 3 inverters that are prevalent in the marketplace today. Because the majority of our business in Atlantic Canada right now, or opportunities, are still residential. We'll talk a little more detail about them. But on the commercial side, you'll still see in the original inverter technologies what's known as a string inverter. So this is DC. You string your modules together anywhere from 5 to 20, depending on the inverter. Could be more with some newer technologies. But essentially, I string those modules together in series. So on the back side of a module, you have a positive cable, you have a negative cable. So I go positive to negative, positive to negative. At the end of, say, that 10 module string, I've got an unused positive cable, an unused negative cable. They go back to my string inverter. The downside of that technology is, because it's series DC wiring, if I have any manufacturing intolerances coming out of the plant, I have degradation over time that varies between modules on that string. I have shading like a cloud on one module. I have a tree branch, snow, anything that could be built up. If a single cell on a single 60 cell module drops in performance, the entire, say, 10 modules on that string drop. Now, in large scale deployments where I may have a megawatt of solar, 10 modules represents a very low percentage of production. So I'm not too concerned on those deployments. It's still the most cost-effective, efficient way, assuming everything's facing the same direction and everything has the same tilt angle. String inverters make a lot of sense. But on the smaller scale side, when I get into residential rooftop deployments where I may have east-west, I may have dormers, I've got modules on the same string that I want to face in different directions, that's where a regular string inverter starts to fail. So what became prevalent in the mid-2000s were microinverters. So move that DC to AC conversion from essential string, put it on the back side of the module, and now I end up with a technology, 2 technologies, one known as max power point tracking and the other known as module level electronics. And now on an install where I only have, say, 10 kilowatts, 30 panels, all of a sudden I'm not worried about the considerations I just talked about with the string inverter: shading, intolerances in manufacturing, degradation over time, or multi-roof angles, because each module is going to perform to its maximum, because now I'm wiring in parallel. It's not affected by the other module. And then in 2015, 2016, we saw a company out of Israel, actually SolarEdge. They took the best of both worlds. So they took the benefits of max power point tracking, they took the benefits of module level electronics, and they came out with a power optimized or DC optimized system. Now I still have DC coming off the roof. I still have a single inverter, but I put power optimizers on the back of each module. And the benefit of that is I maintain my DC series rail voltage, or the optimizers maintain that rail voltage between 380, 400 volts. And if there's any shading issues, everything we mentioned, only one module is affected. So the current coming in from the module to the power optimizers fluctuates, but the DC string voltage maintains its constant voltage. The real benefits are microinverters. You've moved your failure points up onto the roof. You've got inverters up there. They're more costly. You've got an inverter per module. Where power optimizers, you've got small technologies on the back of each module and a single inverter. So less money, less maintenance potentially, but the big benefit right now of power optimizers that we're realizing if we have DC coming off the roof is once we want to implement battery storage, I don't have any of the inversion losses from DC to AC, from AC to DC, and from DC back to AC that I would have with microinverter. So that's the real benefit. Practically, what does this mean in the marketplace? This is a market share graph. So here's SolarEdge and Enphase. These are the two largest manufacturers of those MPPT and MLE, so the PowerPoint tracking and module level electronics that I referenced earlier. This is 2017. Between all the manufacturers who play in residential who offer these technologies, it's over 90% market share for these technologies in the residential marketplace. So that's the modules, that's the inverters. Next, we'll look at the racking, right? We've got our two electronic systems, as I mentioned. Now we need the mechanical aspects. And this is the most commonly used racking system in residential deployments and even some larger commercial deployments in Atlantic Canada. It's the most common roof type we have. It is a slope roof with an asphalt shingle. Very simple to install. The products that are used in this marketplace have been well seeded for a long time, so they're fundamentally sound. They install very quickly, and really all you need are three main components. You've got a flashing kit, you've got your mounting bracket with legs into your rafter, you've got an L bracket coming up off of that, and then you've got the railing itself. And then on top of the railing, you would mount your microinverters and your modules. So very simple to install, very straightforward, most commonly used system in Atlantic Canada. The next one that we see, and it seems to be in pockets depending on your region is metal roof mounting. Once you get off of the roof with your brackets, your L bracket or your S5 bracket like you see in this image, everything else is the same. Rails are the same, attachments are the same, your power optimizers or microinverter mounts are the same, everything's the same. The only difference is how you secure or fasten it. And with metal roofs, there is quite a few options depending on your metal roof. If I was building a new house today or putting a new roof on, I would go with the standing seam. And if you look over here on the right side, you'll see these non-penetrating standing seam S5 clamps. These use pressure, as you can see in this image, to mount to a standing seam. Unfortunately, here in Nova Scotia, standing seam is not that popular. So what we'll see is a flat plate with multiple penetrations like this with some sort of butyl membrane underneath. You'll see a hippo mount to go over that ribbed option. Or what you'll see are these legs and with different spacers on them depending how deep they have to go. Because the issue that some installers find with metal roofs here in Nova Scotia is they'll get strapped over top of existing asphalt roofs. So now to find the truss or the rafter, it's a little more difficult because I've got metal roof strapping, asphalt, then I get into the sheathing of the roof, and then finally into the rafter or truss. A little more difficult. These have neoprene gaskets, so you'll typically see these mounted directly into the strapping, those flat plates, or if you can, the standing seam S5. The next one we've sold and you'll see in this marketplace are flat roof. Very common in commercial, and really they only make sense for commercial. You get into small residential systems, not really applicable because unfortunately with flat roofs, it's economies of scale in the sense you need multiple modules to create a bridging effect to self-support or self-ballast. If you have a small 10 kilowatt deployment on a residential flat roof, you'll need quite a few penetrations to hold that on. Whereas if you interconnect all these modules on a commercial roof, the system gains strength and stability by having more modules connected to it. So this is a south-facing. One thing I want you to keep in mind if you look at this slide is the spacing between rows. So due to shading, I want to keep spacing. So this eliminates some of the density I could have. Also, I also have this wind catch in behind, right? Because if I have hard winds, I need some sort of wind diffuser to stop those panels from lifting, especially here in Atlantic Canada. So an alternate to the flat roof south facing is a east-west racking solution. So the east-west allows for higher density. As you can see, I have no spacing between the rows. And also it eliminates that wind catch. The downside to east-west facing is production. South facing at the right tilt is always going to be my highest production. Plus side to this from a production standpoint is my east panels never produce maximum power when my west panels are, so I can actually use smaller inverters because I don't have the same issue with pure south facing. The last option we'll talk about, and if you have the space, it's a great option. Typically more costly to install than a sloped roof mount because you're getting into footings, helical piles, screw piles, or slab. But from a production and efficiency standpoint, ground mounts are the best because I can pick my angle, I can pick my orientation, and I can even go up from there. So a fixed angle ground mount would be the most simplistic. What you're looking at here is what's called a seasonally adjustable. So I can adjust multiple times throughout the year, summer solstice, winter solstice, as that sun angle changes. Also, these mounts work with 60 and 72 cells like the rest of the racking systems, and I can either do long linear runs, or if I have the room, I can space these out one in front of the other. Just make sure the spacing maintains the correct distance so you avoid shading. So ground mounts are a great option. You can also get into some tracking systems more commonly used in commercial. 3-axis was popular for a little bit. Now you'll see 2-axis that just follows the sunset, sunrise. Last part of the material side is the balancer system. So everything else is a typical distributor product. Outside, maybe what you see here, which is that PV photovoltaic cable rated for 2000 volts DC, also rated to be put directly onto the roof. And then some DC disconnects, AC disconnects are going to be common on the shelf. Everything else, tech cable, RW, conduits, breakers, fuse holders, terminal blocks, MC4 connectors, sorry, that's the only other one that you may want to add to your shelf if you're going to support the market. And really, this is the only product you would want to stock as a distributor to support the market. Everything else would be ordered on a job-by-job basis, the modules, inverters, and racking. So sizing my system, right, we looked at the start at those modules. I referenced wattage, so 60 cells and 72 cells. How many watts do those modules come in? So I reference wattage, but how big of a system do I need? And we don't buy and sell watts, we buy and sell kilowatt hours from the utility. So how do I go from one to the other? Well, you could use some complex math, but luckily someone's already done the work for us. This is what we call a solar irradiance map. And you can see at the top here, production over wattage over time. So on this slider bar, which has the indicator colors, what it's telling you is if I have 1,000 watts, you can see here kilowatts. If I have 1,000 watts of modules, so in the case of the modules we looked at earlier, 333 watt modules, that would equal 1,000 watts. If I had those 1,000 watts at my house, say down here in Liverpool, on average, how many kilowatt hours a year would those 1,000 watts produce? And that's what this is telling you. So down in the Liverpool area, you're going to average 1,120 kilowatt hours per year per 1,000 watts of solar installed. So that's pretty straightforward. Now I can design my system because if I want to size it, here's a copy of a Nova Scotia Power bill, but it's similar in PEI in New Brunswick and Newfoundland. But here's a copy of an energy bill, tells you how many days of use. So I can actually take my previous year, add up all of the days in the year and the kilowatt hours used, and now I can size my system based off that. Because under a net metered program, Some utilities won't pay you for more power produced. So if you end up with a net credit, so I've produced more than I've consumed, that gets washed. Or in the case of Nova Scotia Power, who will pay you, they don't want you designing systems that can produce more than 110% of your consumption. So very important factor in design. And the other nice thing is design has been simplified. So for installers in the marketplace, or for anyone wanting to become an installer, these irradiance maps are built into software. So I can pick a house anywhere in Atlantic Canada, and the software will actually lay out my irradiance potential. This is the software you're looking at here in this slide, known as Aurora, and you're seeing the north-facing roof. It's purple, less solar irradiance potential than that south-facing roof where the modules are laid out. It also will produce shading reports, solstice reports, antilellums. It will do everything you need to do. So we don't have to get too involved these days in calculating production. Software will do it for us. Some other considerations before we jump into installation. What do I need for solar? So rule of thumb, roof less than 10 years old. This is definitely true of asphalt roofs. If you do have a metal roof, this number goes up quite a bit. Service size, we'll get into the math in a second, but a minimum of a 100 amp panel or greater. You want to be able to backfeed the maximum amount of solar that makes sense on your roof. Minimum obstruction, no trees. You know, you get in some of these cities, you'll have some big maples, some big oaks right in front of the house. Unfortunately, those don't help. And in the interest of sustainability, we don't want to be cutting beautiful trees down to get some money out of our roof. Also, aspects, south, east, west facing, those are the best and most common aspects for solar. Of course, north doesn't have much irradiance potential. So let's just jump into quickly the installations. We are, as I mentioned at the start, focusing on grid-tied systems. These installations have been vetted for years and years and years. California has had a solar rebate now for over 20 years. So the product is very easy and quick to use. So this would be the first part of an installation. Once the design is done, the homeowner signs the deal, contractor comes out to make sure the roof looks and will fit what was laid out in design. Next, they mount the stanchions or the brackets with lag bolts to the actual roof. And you can see here, here's your threaded stanchion, here's your two lag bolts. These are gasketed. These go directly into the rafters. Spacing is typically 48 inches. Older homes may require what you see up here, 24-inch spacing, just to balance that weight out on top of the rafters or truss. Once this is in, these legs are gasketed, as I mentioned. Typically, you'll have a silicone over these. The industry did it this way for years. This would be the end of it. It would be watertight. We'd put silicone around the edge and call it a day. But now most installers will use these flashing kits. These kits get pushed up under the course above it. Now I'm protected from water egress above. I've got a bead of silicone in this channel you see here with the pointer, and I'm protected from hard-driven rain from any direction. And the actual stanchion here, the threaded part, does not penetrate the roof. So that's why that flashing kit is so valuable. Once that's on, I can go ahead and put on my L brackets. These L brackets are what will hold the rail. Now, most installers will actually put these onto the rail first. It's easier to work with, but then the rail and the L brackets would go up, and that's the next step, getting my rails on. Once my rails are on, I can start mounting my micro inverters. And then finally, what I would do is the wiring. So you can see my bond wire run here between rails. You can see, in this case, these are power optimizers. Microinverters would be similar. They're all interconnected. And the positive negative feed ins are just waiting to receive the actual modules that will go on top. Then I'd finish up my wiring. So I've got my, this is a DC power optimized system. So I've got my two positive DC wires coming into my fuse holder and are fused to the size of the wire, in this case, number 1030 amp. I've got my terminal block for my for my negatives, and then I've got my bond and ground coming up. Cover goes on, rodent guard goes across over those individual conductors, and then I wire up my inverter here. So we've got those 2 strings, 4 wires coming on the DC side, and now I've got my AC going out to my disconnect switch, which you see here on the outside of the house, from my disconnect back to the panel. And you can also see coming down from the roof, this is PVC, and single conductors run inside that. Some people will use tech or go through the house is another option. And then for final, that's the fun part. Everything is done. Inspectors have approved it. I pop my modules on and they come out one last time to make sure my lamicoids and everything else are done and finalized. So that's what an install would look like in a grid-tied system. Next thing I want to touch on quickly before we finish up is just sizing the system. How does the actual math work? And it's actually quite straightforward. So this is showing the rule, section 64 of the Canadian Electric Code for renewable energy systems. Now, this one here specifically is showing a non-dwelling unit, but dwelling unit happens to work out the same mathematically. But the way the sizing works based on your panel size and your service entrance is I can take 125% of my bus rating, subtract the main breaker rating, and that gives me my photovoltaic size that I'm able to go with. So let's just walk you through a real world example. So if I had a 100 amp main breaker on a 125 amp bus, I would multiply that 125 amp bus by 1.25. I get 156 amps. Subtract the main breaker rating of 100 amps, and I get 56.25. The closest breaker to 56 amps is going to be 50 amps, and then because I can only backfeed 80% in residential, that means my breaker is rated at 50, but my AC inverter can only be 40 amps, and then 40 amps times 240 volts equals 9.6 kilowatts. So this holds true for both 100 amp services and 200 amp services. Now there are some workarounds for this. If you wanted a larger system, you could go ahead and put a dual lug meter base on and backfeed the solar array directly into the dual lug meter base. You could also do a splitter trough scenario. So in a 200 or 400 or even 100, you could feed from the meter into your splitter trough and use the bus rating of that splitter trough, then feed your main service panel, and then run a utility rated fuse disconnect into your splitter trough. So there are some workarounds, but workarounds cost money. This is the most cost-effective way to do it. When homeowners are putting solar on their home, they're doing it because they want to make a return on that investment primarily. So keeping installation costs down is key. The other thing I want to touch on, because that slide only referenced AC inverted backfed power, I want you to keep in mind there is something known as oversizing. So I can have more DC, so modules on my roof or ground, than I can have AC inverted that's backfed into the utility. And the reason I can do that is for a couple reasons, but I'll just show you here quickly. When you look at a module, so a 300 watt module, a 400 watt module, we talked about earlier, its wattage is based on standard test conditions, 25 degrees Celsius, wind blowing across them, cooling them. In the real world, operating conditions are far different than standard test conditions. Also, inverter manufacturers build in oversizing ratios. So if it's a 100 kilowatt inverter, they may say there's a 25% oversizing ratio. So I could have an extra 25% DC, and it's for several reasons, but this is one of them, because the chances that those modules will actually perform to their maximum potential are very rare. And if they do, say a nice sunny April day like we're having up to until today because it's snowing, but on the weekend we had some beautiful days, it was nice and cool. And okay, so those modules may have produced their maximum. Worst case scenario, the inverter will just do what's called clipping it. So it will never, over output it, and you will never overdrive it. But this is the real reason, because most modules will never perform to their standard test conditions. They'll perform to their typical operating conditions. And that's why we oversize. And that is solar installations, fast and info packs. So some frequently asked questions. What is the average cost of install? Pricing on all of these components and installation is typically done on a per watt basis. So the average cost of install right now, this is actually published on the Efficiency Nova Scotia website under the Solar Homes program. It's around $2.90 a watt. Tax in. So that's what the average homeowner right now would be paying. That drops significantly as you go up in size. Is a special certification required to install solar? The answer to that one is no. You do need to have an electrical ticket to pull a permit to install solar. So the answer is no, but if you want to access the rebates available currently in Nova Scotia and Prince Edward Island, you do need some level of certification or proof of competency. So that's something to keep in mind because you need those rebates to be competitive. What should I stock to support a solar contractor? Well, I mentioned it earlier. It's really those balance of systems. Don't worry about modules, inverters, racking. You can buy those as a lot per job. Most people would have a relationship already to buy them. So really, if you want to do well as an electrical distributor right now and not get into the volatility of all the components, just focus on those balance of system components we looked at. I didn't see road and guard around the array. Is it required? This really came up because the Ontario market, it's code. So right now we only require road and guard or some sort of cable protector on the individual conductors exposed on the roof. In other markets like Ontario, which was the largest for a long time, they actually require a meshing around the entire array so animals and critters can't get under there. We do not require that currently in Nova Scotia. And I know we're just 1 minute over, but manufacturers, so we do rep manufacturers in this space, IMO and Soltection by Vanke. Those are both distributed through FuseTech here in Canada. We also have Service Wire, one of the largest providers of PV cabling in the market. And then on the solar side, we're selling Canadian Solar, Solar Edge inverters, and kinetic racking.